In this video, we're going to continue working with 6.7, and we're going to talk more about in behavior of polynomials, as well as just analyzing the graphs. So a turning point, we talked about number of turns in the last section, but turning point is where the graph changes from increasing to decreasing. And we call that point of change a local minimum or a local maximum, depending on which way it's going. So if the degree is n, remember it can have at most one less than that in the number of turns or the number of extrema. So what we call minima and maxima, that's the plural for minimum and maximum. What we call those collectively is extrema. Local extrema are when the ends are going forever in opposite directions, so the range is all real numbers. But if the range is not all real numbers and we have a overall low point or an overall high point, we call those absolute minima or maxima. So for example, a quadratic, it has an absolute minimum or maximum because it has a peak where the graph is not going to go beyond. A cubic just has a local min or max where it changes direction, but it does not have an absolute. So again, if the range is all real numbers, it is not going to have an absolute max or min, and that happens when it's an odd degree. Okay. All right. So when we're talking about these mins and maxes, when we ask you to identify what is a minimum or maximum value, we want you to give the y coordinate. Okay. So if I'm looking at this graph here, the local minimum, so that's a low point on the graph, is right here. So this point has the coordinates 2, -5, okay? So the local min is the y value there, which is -5. The local max, so anytime I have a hill, so min is valley, max is hill. This one has a, oh sorry, that should be -2, -5. This one has a coordinate of 2, 4. So the local max has a value of 4. Okay, so intervals of increase and decrease, you have learned about this before, but we're going to talk specifically about the notation. So interval of increase, so anywhere the graph is rising from left to right. So from my local min to my local max, it is increasing, it's going up. So whenever we do intervals of increase and decrease, we use x values only. So it is increasing from here to here, but I'm only going to use the x values, and I'm going to use parentheses. So from -2 to 2, it is increasing. Okay. Intervals of decrease, we do the same thing. It's still x values only, but it is decreasing from up until -2, and then again from 2 on. So leading up to -2, that's -infinity to -2. And then we're going to use our union symbol. Or you could use a comma, but actually, yeah, I'm just going to do a comma, you guys. It is increasing here, and it's increasing again from 2 on, so that's from 2 to +infinity. So we always use parentheses, and we only use x values. The reason we don't include those values, you guys, because that's the point where it's actually changing from increasing to decreasing, so it's neither. So we don't include it in either interval. Okay, so now we're going to look at another graph, okay? Domain, this one is going to be all reals. Range, okay, so the low point on this graph is from -1, and then it moves up. So we do have a point, or not -1, +1, excuse me, y value of +1 up to infinity. So our local maximum is anytime we have a hill. So I have a hill right here that has a y coordinate of 2. Local minima, so we have 2 of those, okay? But they both occur at the same y value of 1, which is also we can also say this is an absolute because it's the overall minimum of the entire graph. Nothing goes below 1. So we can call it local because there's 2 different ones, but it's also the absolute minimum value. Okay, interval of increase. So where is our graph rising from left to right? So that's here to here. and then again here to here. So we're going to use parentheses and only the x value. So the x value here is -1 up until the hill. X value at that point is 0. Okay, next time it starts to increase is when x is +1 and then on. So 1 to infinity. Okay, decrease this far left section and from the hill to that local min. So -infinity up to -1 is this section, again the x values, and here from x is 0 to x is +1. Okay, all right, end behavior. So we talked about this in our last section, but this is what we want to know the ends are doing. So as x approaches -infinity, so that is referring to the left side of the graph. What are our y values doing? So on the left side of the graph, my graph is shooting up to +infinity. On the right side, where x is approaching +infinity, our graph is also going up. Okay, so based on this graph, my ends are going the same direction, so my leading, and they're both going up. So the right side going up means my leading coefficient is positive, and because they're going the same direction, it must be an even degree. Okay, we're going to do some more graph analyzing here, you guys. All right, domain of this one, also all reals. And my range is going to be all reals because of those opposite ends. It's going to include every y value. Local maximum, okay, is right here. That has the point 2, 3. Some of the y value there is 3. Local min is right here, which is -2, 0. So 0 is the local min. Neither of these are absolutes because they're not overall maxes or mins, because I'm going to go below -2 here and above 3 here. Intervals of increase. So it's only increasing from -2 to 2. And it is decreasing from -infinity to -2 and from 2 to infinity. Okay, on the left side of the graph, as x approaching infinity, my f of x is approaching infinity. On the right side, my graph is going down to -infinity. Because the right side is going down, the leading coefficient is negative. And because the ends are opposite, it is an odd degree. The y-intercept we can see on this graph is 2. I'm going to just put the ordered pair, 0, 2. The real roots, it looks like we have 2 of them. This one has a multiplicity of 2 though, because it bounces. This one has a multiplicity of 1, but I only see it crossing 2 places. So this one, I'm going to change that. I'm going to say 3 real roots, because this one occurs twice. So 3, this one, I'm just going to point out multiplicity of 2. Okay, so the number of turns, it has 1, 2 turns. So the minimum number, 2 turns. So the minimum degree of the equation it could be is 3, right? The number of turns is always 1 less than the number of turns. If that's the max, then the degree could be 1 more than that maximum, okay? All right, another one here. All right, domain, all reals. Range, looks like we have a low point at -4. Okay, so local max, anytime I have a hill, so here 5, looks like just 5. Local minima, we have 3 and 4, and -4, but this one is an absolute because it's the overall minimum of the entire function. Interval of increase from -5 to -2. I'm looking at just the x values. Again, from 1 to 4. And from 6 on. Okay, intervals of decrease, negative infinity up to -5. Here from -2 to 1. And from 4 to 6. All right, end behavior. On the left side, as x approaches negative infinity, my graph is going up to positive infinity. On the right, as x approaches positive infinity, so does f of x. On the right side, it's going up, so my leading coefficient is positive. My ends are going the same direction, so it's even. Y-intercept, this one's not a great estimate. I'm just going to say approximately, what, -3.5? Okay, real roots, I see it crossing twice, and it's going straight through, so I only see 2 real roots. The number of turns, there's 1, 2, 3, 4, 5 turns. So the minimum degree the equation could be is a 6th degree. All right, that is it for 6-7 day 2.